recasting problems into the standard form. So this is the loop that we have when we have additive uncertainty. So now we've closed the loop. So remember that our small gain theorem that we just discussed included the fact that we had some g of s that included the plant, it included the k, it included the w, and so we want to be able to put this into a standard form so that we can use the theorem that the small gain theorem the way we presented it. So the question is, how do we put something like this into this form? And the critical thing here is really the theta and the psi. That is, because remember that it was the transfer function from theta to psi, m, that was useful in assessing stability. Okay, so in particular, we need the input and the output of the uncertainty. So over here, that's the input to the uncertainty, and over here is the output to the uncertainty. So what we can do then is we can do the following. We can ignore the w and the z here. We can ignore the r and the y because we're primarily concerned again with this transfer function and to this transfer function. So I'm going to take this diagram now and I'm going to redraw it. Okay, so in order to define the transfer function m of s, so I've basically taken this diagram. This is now my input, this is now my output. Okay, so here's my input, here's my output, here's the feedback through delta, and so this is just a redrawing of that, just kind of rearranging things without actually changing any of the algebra here. And so we have this is our controller m. So all of this now is our controller m. So by redrawing the diagram, we can put it into this form, into the loop like this. And so our system is stable if this loop is stable. So it's not that the other transfer functions don't exist. Remember we had j, l, m, and n. Those other transfer functions still exist, but m was the one that determined the overall stability. So we're assuming that when we chose a k in our feedback loop, that k made the system stable. And so we are assuming that's stable. And so now we have this this transfer function, and this transfer function should be stable. This gives us m of s. So if I just look at this quantity now, this quantity has this transfer function. And I can actually express it two ways because it's a matrix. I can either have the k on this side, in which case I have p naught k, or I can have the k on this side, k p naught. So those are the two options that we have. So that's the additive uncertainty. So we've seen now how to recast the additive uncertainty problem into the standard form. For the multiplicative uncertainty, this is one of the forms that we have for multiplicative uncertainty. And so again, we want to redraw this diagram. And so notice that we've wrapped our control loop around this. So we have our controller here. We can redraw our diagram. So notice here I have psi, here I have theta. I'm going to redraw this so that this is my input, this is my output. I'm going to ignore y, I'm going to ignore r, and so this is the diagram that I get. So remember that the uncertainty actually wraps around this. So this is the quantity m, and the m has this transfer function. Okay. So we can go through and derive this transfer function from this block diagram. So you're maybe asking, well, now how do we do that again? So you would, the way I normally do that is I start with the output of my summer. Okay, so let's call that E. So E is equal to W times theta plus psi. So I start there. Next, I write an equation for psi. Psi is equal to minus K times P times E. And so I have two equations that involve E and psi. And so basically I solve those two equations for the two unknowns. Actually, I don't need both unknowns. I only need the psi. And so I can solve for C, and that will be a function of theta. And this is what we get. And again, I can express it in two different forms. So using a matrix inversion lemma, I can put this on this left side, or I can have it on the right side here. So that's multiplicative uncertainty 1. Multiplicative uncertainty 2 is similar in that this and this combination are interchanged. And so again, we can redraw the diagram. This is our diagram. We can get the transfer function for it from this. And so we can recast the multiplicative uncertainty 2 into this form. Feedback uncertainty. So in this case, we have this kind of feedback uncertainty. So again, I consider this as my input, this is my output, I ignore this and that, and I can redraw it and I get this form. Okay, and this has this transfer function. So that's feedback uncertainty 1. Feedback uncertainty 2, I have it now on this side. So this connection and this are interchanged. So again, this is my input, this is my output. I redraw the diagram. This is what I get. From this, I get this model, M. And finally, feedback uncertainty 3, where I'm actually feeding back my uncertainty around my nominal plant. Okay, so in this form then, I have, again, I treat this as my input, that is my output. I redraw the diagram. This is what I get. And when I look at the transfer function, this is the transfer function I get. So I have shown a number of ways of going from various uncertainty forms and recasting them into the standard form so we can evaluate whether or not the system is robustly stable or not. Okay, so that's what we have, and so this is the transfer function that we have in this feedback uncertainty case. So once we know M of S for our given uncertain system, then we can work with the small gain theorem. Now, small gain theorem is not the end-all. And where the small gain theorem fails is if we have additional information about the uncertainty. So, for example, the uncertainty has structure to it. So, in the cases we've been looking at, our uncertainty is a matrix. Okay, and so in general, the matrix. Remember, we're looking at all deltas that satisfy those things, but if we restrict our attention within delta, so for example, if delta is diagonal, then the other insert. So the diagonal is a special case of a full matrix, and so we can actually get better results if we are able to consider uncertainties that are diagonal. Or another example would be, for example, that we know something about phase information. So, for example, suppose we know that we have a time delay in our system. We can incorporate that into our phase information. So this is the bottom line is that the small gain theorem fails if we have extra information about the uncertainty. So in other words, the system is really not as uncertain as we thought. And so we can actually do better if we know and can incorporate the additional knowledge about the uncertainty. Okay, so what's the difference between multi-input and single input, single output? Basically the same. It's the same kind of approach. In both cases, we saw that we had a small gain theorem. In a multi-input, multi-output case, we use the singular value instead of just the magnitude. If we have multiple uncertainties, then we would use the structured singular value. Okay, so instead of just the singular value, we now use the structured singular value. So that's what we have. So now we are poised to be able to handle systems with uncertainty and analyze whether or not the system is robustly stable or not.